Hello students, today we will discuss the principles of chemical thermodynamics, and in this section we will be discussing the concept of free energy, enthalpy and entropy with respect to biological systems. Bioenergetics or biochemical thermodynamics is a quantitative study of energy transduction that occur in living cells and the nature and function of the chemical processes underlying these transductions. Cells are chemical systems that must obey all chemical and physical laws. The transformation of energy, its storage, and its use are central to the economy of the cell. You know that several forms of energy are important in biological systems. There are two principal forms of energy, which is kinetic energy and potential energy. Now let's look at some of the examples of these two types of energy. Thermal energy or heat is a form of kinetic energy, the energy of the motion of molecules. For heat to do work, it must flow from a region of higher temperature to one of lower temperature. Although differences in temperature can exist in between the internal and external environments of cells, these thermal gradients do not usually serve as a source of energy for cellular activities. The thermal energy in warm-blooded animals is used mainly to maintain constant organismic temperature. This is an important homeostatic function because the rates of many cellular activities are temperature dependent. Let's look at the example of kinetic energy. One is radiant energy. Radiant energy is the kinetic energy of photons or waves of light and is critical to biology. Radiant energy can be converted to thermal energy when light is absorbed by molecules and the energy is converted to molecular motion. Radiant energy absorbed by molecules can also change the electronic structure of the molecules, moving electrons into higher energy orbitals where it can be later recovered to perform work. For example, during photosynthesis, light energy absorbed by pigment molecules such as chlorophyll, pigments, is subsequently converted into energy of chemical bonds. Next is mechanical energy. It is a form of kinetic energy in biology resulting from conversion of stored chemical energy. For example, changes in the lengths of cytoskeletal filaments generate forces that pull or push on membranes and organelles. Now, the next type is electric energy. Electric energy is the energy of moving electrons or other charged particles and is yet another form of kinetic energy important in membrane function, especially in neurons. Now, several forms of potential energy are also biologically significant. Now, let's look at some of the examples of potential energy. The chemical potential energy stored in the bonds connecting atoms and molecules play a central role in biology. We recognize this energy when chemicals undergo energy-releasing reactions. For example, the high potential energy in the covalent bonds of glucose can be released by enzymatic conversion in cells. This energy is harnessed by the cells to do many kinds of work. A second biologically important form of potential energy is the energy in a concentration gradient. When the concentration of a substance on one side of the barrier, such as a membrane, is different from that of the other side, a concentration gradient exists. all cells form concentration gradients between their interior and exterior fluids by selectively exchanging nutrients, waste products, and ions with their surroundings. Now, a third form of potential energy in cells is an electric potential, the energy of charge separation. For instance, there is a gradient of electric charge of approximately 200,000 volts per centimeter across the plasma membrane of almost all cells. Now, all biological systems conform to the laws of thermodynamics. Let's look at the first law. The first law of thermodynamics states that the total energy of a system, including its surroundings, remain constant. It implies that within the total system, energy is neither lost nor gained during any change. However, energy may be transferred from one part of the system to another or may be transformed into another form of energy. In living systems, chemical energy may be transformed into heat or into electrical, radiant, or mechanical energy. In photosynthesis, the radiant energy of light is transformed into the chemical potential energy of the covalent bonds between the atoms in a starch molecule. In muscles and nerves, chemical potential energy stored in covalent bonds is transformed respectively into kinetic energy of muscle contraction and the electric energy of nerve transmission. In all cells, potential energy released by breaking certain chemical bonds is used to generate potential energy in the form of concentration and electric potential gradients. Similarly, energy stored in chemical concentration gradients or electric potential gradients is used to synthesize chemical bonds or to transport molecules from one side of the membrane to another to generate a concentration gradient. The latter process occurs during the transport of nutrients such as glucose into certain cells and transport of many waste products out of the cell. Now let's look at the second law of thermodynamics. It states that the total entropy of a system must increase if a process is to occur spontaneously. It means the natural tendency of any system is to become more disordered. That is, in all natural processes, the entropy of the universe increases. So let us study the three thermodynamic quantities that describe the energy changes occurring in a chemical reaction. First is Gibbs free energy. It is named after J.W. Gibbs and it expresses the amount of energy capable of doing work during a reaction at constant temperature and pressure. A chemical reaction occurs spontaneously when the free energy of the products is lower than the free energy of the reactants. So, in case of a chemical reaction, the free energy change, which is denoted by delta G, is given by delta G equals to free energy of products minus the free energy of reactants. The relation of delta G to the direction of any chemical reaction can be summarized in three statements. When a reaction proceeds spontaneously with the release of free energy, delta G has a negative value. And the reaction is said to be exergonic. A reaction with negative delta G is called thermodynamically stable. Secondly, in endergonic reactions, the system gains free energy and the free energy change is said to be positive, which is greater than 0. That is, the forward reaction will not occur spontaneously. Energy will have to be added to the system in order to force the reactants to become products. So this is an endergonic reaction. Number 3. If the value of delta G is 0, it means both forward and reverse reactions occur at equal rates and there will be no spontaneous net conversion of reactants to products or vice versa. It means the system is at equilibrium. Now let's discuss the second term, enthalpy, which is denoted by the letter H. Enthalpy is the heat content of the reacting system. It reflects the number and kinds of chemical bonds in the reactants and products. When a chemical reaction releases heat, it is said to be exothermic, and the heat content of the products is less than that of the reactants, and delta H has, by convention, a negative value. Reacting systems that take up heat from their surroundings are endothermic, and in such cases, the delta H has a positive value. Entropy, which is denoted by the letter S, is a quantitative expression for the randomness or disorder in a system. When the products of a reaction are less complex and more disordered than the reactants, the reaction is said to proceed with a gain in entropy. Many biological reactions lead to an increase in order and thus a decrease in entropy. A good example is the reaction that links amino acids to form protein. A solution of protein molecules has lower entropy than thus a solution of the same amino acids unlinked, because the free movement of amino acids is more restricted when it is bound into a long chain than when it is not. Thus, when self-synthesized polymers such as proteins from their constituent monomers, the polymerizing reaction will only be spontaneous if the cells can efficiently transfer energy to both generate the bonds that hold the monomers together and overcome the loss in entropy that accompanies polymerization. Often, cells are able to do this by coupling such entropy-lowering reactions with independent reactions that have a very highly negative delta G, or free energy change. The units of delta G and delta H are joules per mole or calories per mole. Units of entropy are joules per mole per Kelvin. Because of all forms of energy are interconvertible, they can be expressed in the same units of measurement, either joule or calorie. And we know that 1 joule equals to 0.239 calorie. They are interconvertible. 1 calorie equals to 4.184 joules. A calorie is the amount of energy required to raise the temperature of 1 gram of water by 1 degree Celsius. Under the conditions existing in biological systems, including constant temperature and pressure, changes in free energy, enthalpy, and entropy are related to each other quantitatively by the equation delta G equals to delta H minus T delta S, in which delta G is a change in Gibbs free energy of the reacting system, delta H is a change in enthalpy of the system, T is the absolute temperature, and delta S is a change in entropy of the system. By convention, delta H has a positive sign when entropy increases, and delta H has a negative sign when heat is released by the system to its surroundings. Either of these conditions, which are typical of favorable processes, tend to make delta G negative. So delta G of a spontaneously reacting system is always negative. Heterotropic cells acquire free energy from nutrient molecules, and photosynthetic cells acquire it from absorbed solar radiation. Both kinds of cells transform this free energy into ATP and other energy-rich compounds capable of providing energy for biological work at constant temperature. Now let's look at the second law of thermodynamics. It states that the entropy of the universe increases during all chemical and physical processes, but it does not require that the entropy increase take place in the reacting system itself. The order produced within cells when they grow and divide is more than compensated for by the disorder they create in their surroundings in the course of growth and division. In short, living organisms preserve their internal order by taking from the surroundings free energy in the form of nutrients or sunlight and returning to their surroundings an equal amount of energy as heat and entropy. So that's all that we have to learn today. Let's look at some of the points that we have covered. Living cells constantly perform work. They require energy for maintaining their highly organized structures, synthesizing cellular components, generating electric currents, and many other processes. There are two main forms of energy: kinetic and potential. Thermal energy, radiant energy, mechanical energy, and electric energy are the forms of kinetic energy in biological systems, while examples of potential energy are chemical potential energy, electric potential energy, and energy in a concentration gradient. Bioenergetics is a quantitative study of energy relationships and energy conversion in biological systems. Biological energy transformations obey the laws of thermodynamics. The first law of thermodynamics states that energy can neither be created nor destroyed. However, it can be converted from one form to another. And the second law of thermodynamics states that the natural tendency of any system is to become more disordered, that is, for entropy to increase. So all chemical reactions are influenced by two forces: the tendency to achieve the most stable bonding state, for which enthalpy H is used as an expression, and the tendency to achieve the highest degree of randomness, expressed as entropy S. The net driving force in a reaction is delta G, the free energy change, which represents the net effect of these two factors in the equation delta G equals to delta H minus T delta S. And that's all for today. Thank you.